In this video, I will show you how we can verify a given function is a solution for a homogeneous differential equation, and then we find the particular solution for a non-homogeneous differential equation. The given differential equation is x, y, double prime minus 1 plus x, y prime plus y equals x squared e to the 2x, and the given functions are x and x plus 1 and e to the x. First, we want to prove that these two functions are the solutions for the corresponding homogeneous differential equation to this given equation, and then we want to find the particular solution for this non-homogeneous differential equation. First, note that the corresponding homogeneous differential equation is this equation, xy double prime minus 1 plus xy prime plus y equals 0. We set the equation equals 0, and this is the homogeneous differential equation. And first we want to prove that these two functions are the solutions for this homogeneous differential equation. We have to plug in this and then this in the equation and prove that this makes this expression equal 0. Let us start with y sub 1. X plus 1. X times second derivative of x plus 1. So first we have to find second derivative of this expression. The second derivative of x plus 1 is 0 because derivative of x is 1. Second derivative of 1 is another derivative of 1 is 0. So second derivative of x plus 1 is 0. Minus 1 plus x times y prime. If we take derivative of x plus 1, the first derivative of x plus 1 is 1 because derivative of x is 1 and derivative of 1 is 0. Plus the y itself plus x plus 1. This should be equal to 0. Let's see if this is really 0 or not. This is 0. We have minus x plus 1 plus x plus 1. So this is really equal to 0. So this shows that this is a solution for the homogeneous differential equation. Now we have to check the other function. X times second derivative of e to the x is again e to the x. Because derivative of e to the x is e to the x, so second derivative of e to the x is also e to the x. Minus 1 plus x y prime. Derivative of e to the x is e to the x, and plus the y, which is e to the x. This is x e to the x. Here we have minus e to the x minus x e to the x plus e to the x. The terms cancel each other, so this is also another solution for the differential equation. So now we know that these two functions are the solutions for the homogeneous differential equation. Let's find the particular solution for this differential equation with the method of variation of parameters. For finding the particular solution for second order non-homogeneous differential equation, we use this formula. Negative y1 integral of y2 f of x over Wronskian of y1 y2 dx plus y2 integral of y1 f of x over Wronskian of y1 and y2 dx. We use this formula for finding the particular solution. Note that in this formula, y1 and y2 are these two given functions in this question. Usually we are finding the functions y1 and y2 with the method of characteristic equation, but here the solutions for the homogeneous differential equations is given in the question. So y1 and y2 are given. F of x in this formula is the function in the right side of the equation, but it's very important. This is not actually f of x in this question. F of x is the expression in the right side of the equation, but if the coefficient of y double prime is 1. So, to use this formula, always make sure that the coefficient of y double prime is 1. Otherwise, the answer that you get from this formula is not correct. So the first step before we use this formula is to make the coefficient of y double prime 1. And to do so, we divide both sides by x to get rid of this x here. If we divide left side and right side of this equation by x, then we have this equation. So we divide every term in the left and every term in the right by x. Then we have y double prime minus 1 plus x over x y prime plus 1 over x y equals, if we divide this by x, x e to the 2x. Now this is f of x. But what is Wronskian? Probably you are familiar with Wronskian in this formula. But if you don't remember what is Wronskian, let me tell you what is Wronskian of two functions in general. Wronskian of two functions like y1 and y2 is defined like this. Put the two functions y1 and y2 in the first row in the determinant and put the derivative of them in the second row, y prime 1 and y prime 2 in the second row. Then by finding the value of this determinant, you can find the Wronskian. For finding the determinant, we multiply y1 by y prime 2, y1 times y prime 2 minus y2 y prime 1 minus this times this. So this is the formula that we can use for finding the Wronskian. Here the two functions y1 and y2 are x plus 1 and e to the x. So let's find the Wronskian here. Wronskian of x plus 1 and e to the x is x plus 1, e to the x. Derivative of x plus 1 is 1 and derivative of e to the x is e to the x. If we multiply them like this, this equals x plus 1 times e to the x minus e to the x. Here, if we simplify this, we have x e to the x plus e to the x. And then we have minus e to the x. So finally, this equals to x e to the x. This is the Wronskian in this example. Now let's find the integrals that here we have. Let us start with this one. Integral of y2. y2 is e to the x times by f of x. Note that this is f of x. X e to the 2x over Wronskian, which is x e to the x. Now note that x from the bottom and x from the top cancel each other, and e to the x and e to the x cancel each other. Only e to the 2x remains in top. An integral of e to the 2x dx is e to the 2x over 2 or 1/2 e to the 2x. And please do not add c here. When you are finding these integrals, do not add the constant c. Let's find the other integral. Integral of y1. y1 is x plus 1 times by f of x. F of x is x e to the 2x. Here we have f of x over the Wroński. X e to the x dx. We can cancel one x from the bottom with x from the top. And e to the 2x over e to the x is e to the x. So this equals integral of x plus 1 e to the x dx. For finding this integral, you can use integration by parts method. If you use the integration by parts method, easily you can see that this integral equals x e to the x. Let me show you why. For finding this integral, if we use the integration by parts method, we can choose this to be u and dv equals e to the x dx. If we take integral from dv, v is e to the x, so we integrate this and we differentiate this. The derivative of x plus 1 is 1 or 1 dx actually. So we differentiate here, we take derivative here and we integrate in here for finding v. Now based on the formula of integration by part, this integral equals u times v. U is this, so x plus 1 times v e to the x minus integral of v du is dx. But integral of e to the x dx is again e to the x. Note that this is x e to the x plus e to the x. Minus this e to the x cancel each other, only this remains, as I mentioned here. So this integral equals x e to the x. Now that we have the value of integrals, we can find the particular solution from this formula. The particular solution is negative y1. y1 is x plus 1, so negative x plus 1 times by the first integral that we found here, 1/2 e to the 2x plus y2. y2 is this, y2 is e to the x times by the other integral, x e to the x. Let's simplify the particular solution. You can leave it in this form, but it's better to simplify it. If you multiply x plus 1 in the bracket, and don't forget we have a negative here, we have negative 1/2 x e to the 2x minus 1/2 e to the 2x plus x e to the 2x. Note that if we multiply these two, we have x e to the 2x. Here we have minus 1/2 x e to the 2x. Here we have plus 1 x e to the 2x, which if we add them, we can write it finally as. So if we add this to this, we have 1/2 x e to the 2x minus 1/2. Let's write this term here. So this is the particular solution for this given differential equation. So this is y particular. I hope by watching this video you have learned how we can find the particular solution for a non-homogeneous second order differential equation. If you liked this video, please subscribe in my channel.